Hey, welcome to Lesson 9.5, Functions and Their Inverses. In today's lesson, we're going to be covering these two learning goals. Number one will be determining whether the inverse of a function is, in fact, also a function. So we'll be looking at inverses of functions and see if they are functions. And we'll be writing rules for inverses of functions. Now, we just finished up looking at different operations with functions, and one of the operations was composition of functions. And we're going to find that we have a new use for the operation of composition in this lesson. We're actually going to be using composition of functions to verify whether two functions are in fact inverses of each other. So let's take a step back and see what we already know about whether something is a function or not. So you may remember that to be a function, each x value must be paired with exactly one y value. In fact, that's exactly why when we were studying square root functions, we restricted the domain to just the positive values and 0, because otherwise when we take the square root of a positive, or I guess I should say non-negative real number, other than 0, so positive real numbers, we always would get two solutions, a positive and a negative. So we restricted the domain on the square root function because if we didn't, we would get two outputs for a given input. So if our input was, say, 64 and we were taking the square root of it, we would get 8 or negative 8, which would actually violate that rule for a function that it has to have, for a specific input, it has to have a unique output. Just, in other words, just one output. Now, another thing we know about functions and things that, how do we know if things are functions? We know that graphs of functions all pass the vertical line test. So, for instance, if I wanted to know if this function here with this kind of squiggly graph, call it f of x, if I wanted to know if it was actually a function or just a relation, I want to see, does it actually pass the vertical line test? So, and I can see that at any point along the graph, I can drop down a vertical line and it's only going to hit in one spot. So that's how we know graphically if something is a function. So that's what we know about functions. What do we know about inverses? Well, we know that inverse operations, they undo each other. For instance, squaring undoes square rooting and vice versa. Multiplying undoes dividing and so on. Those are inverse operations. An inverse's graph is a reflection across the line y equals x. So that was one way we used to verify that in fact that these relations were inverses of each other, was by looking at their graphs and see if the graphs were in fact reflections of each other over that line y equals x. Now notice I was careful to say whether they were inverses. I didn't say inverse functions, I just said inverses, and I mentioned, instead of saying functions, I said relations. And that's because an inverse of a function may not actually be a function. Or something that's not a function, when we look at its inverse, it could be a function. Well, we've even looked at writing the rules for inverses of some functions that we know, like linear functions and things like that. And remember, we did that by just switching x and y. And then usually the next step was to solve that back for y so that we could put it in that function notation f of x, or f inverse of x if it was the inverse. And then you may remember that because we switch x and y, then that means that the domain and range are also reversed. So the domain and range of inverses are switched. So let's say we have some sort of function and we want to know if its inverse would also be a function. Well, one way we could find that out is to actually take that function, write the rule for its inverse by switching x and y and solving for y, and graph it. Or we could just simply take the points of the original and reflect them over y equals x and see if that new graph passed the vertical line test. But that all seems like it's got quite a bit of work to it. Well, there's a test that we can use that doesn't really involve us having to look at the graph of this new inverse function, inverse relation at all. We can just simply look at whatever the original function is, and we'll be able to tell if its inverse will also be a function. And that thing's called the horizontal line test. So we know vertical line test. Remember I said vertical line test was, like my little example up here, is we look to see if that relation that's graphed itself is a function. But if we use the horizontal line test, we can tell if the inverse of whatever graph we're seeing will be a function. So here's an example. And I guess to clarify this in words, it means if any horizontal line passes through more than one point in the graph, so now we're looking at horizontal lines, and if it passes through more than one point on the graph, of a relation, then the inverse is not a function. So if it passes through more than one point on the graph of relation, then the inverse is not a function. So this horizontal line test is not telling me specifically something about the graph I see, but the inverse of the graph I'm looking at. So that allows us, without actually having to graph the inverse, to know if it would be a function. And if you think about this, if we took a horizontal line and we reflected it over the line y equals x, it would become a vertical line. So in effect, this is allowing us to do the vertical line test without actually having to graph the inverse relation. So here's a couple examples. So I'm looking at this first right here, this first graph, and I want to know if the inverse of this thing would be a function. And notice it does pass the horizontal line test, and so the inverse is a function. This next one, this graph fails the horizontal line test. In fact, at every point except for one, it fails. And so the inverse of this thing would not be a function. And actually, if you think about what the inverse of that would be, remember that's a quadratic, and so the inverse of that would actually be some sort of square root function. That's exactly why we have to restrict the domain on square root functions to make it actually be a function. And if we did that here, that would, we restricted the domain, we would just see half of the branch of this parabola, and then when it was reflected over y equals x, you'd see that it actually would be a function. So when a relation and its inverse are both functions, the relation is called a one-to-one function. And mainly the reason why they call it a one-to-one function is that for both the original and its inverse, one input means one output. That's how you know if something's a function. For a unique input, there's a unique output. So let's take a look at an example of using the horizontal line test. So it says determine whether the inverse of the relation below is a function. Well, the original, this thing right itself, this graph, I can tell is a function. This graph passes the vertical line test. But I want to know about the inverse of this. So I don't have a rule for this. So I can't write like the equation or the rule for the inverse by switching x and y. Looks like it would be pretty difficult to reflect it over the line y equals x, although I could pick a few points and see if I could kind of sketch it. But I don't need to do all that because now I have the horizontal line test. Horizontal line says if a horizontal line only intersects one point on a graph at any point along it, then its inverse will be a function. This thing fails, so it fails the HLT, horizontal line test. So I would say that f of x, the original relation that you see here, is a function. But f inverse of x, the inverse of this relation, is not a function. So horizontal line test is really just a test not on the specific graph that you're seeing, but on its inverse. Let's go ahead and turn the page. So we're going to have a couple you-try questions for B and C. And so I want you to pause the video now, look at the graphs given in B and C, and use the horizontal line test to determine whether the inverse of each of these relations is in fact a function. So please pause the video now and determine if the inverse of f of x in both of these examples are functions themselves. So we're in luck. Both of these are functions. F inverse of x is a function in both example B and C, and the support that we could give to our claim that they are that their inverses are functions is that they pass the horizontal line test. Okay, so example 2, we're going to be writing rules for inverses. So example A says, find the inverse of f of x is equal to the cube root of x plus 1. Determine whether it is a function and state its domain and its range. So first of all, I could think about what this graph looks like, and then I could worry about writing its inverse. But I know that this graph is a cube root graph, so it's kind of like that little S, stretched out S curve. And the plus 1 underneath the radical means it's actually moving 1 to the left. So it would kind of look sort of like this. And so I know that when I write the inverse here of this function, I know that it is going to be, it's going to be itself be a function too. So it passes the HLT, the horizontal line test, so that means that f inverse of x will actually be a function. And so I'd say f inverse of x is a function. So let's actually write that function. So we start off and we take the original function, which was f of x is equal to the cube root of x plus 1, and we replace f of x with y, and then we're going to switch x and y around. So if I were to actually erase out f of x and put in place of it y, and then I was going to switch out x and y, I would rewrite it as x is equal to the cube root of y plus 1. And now I have to solve for y, which means I've got to get y all by itself. Well, the first thing I'm going to have to do is get rid of that cube root over top of it. So I know that to undo cubing, I would have to cube both sides. So if I cubed the right-hand side, that would just cancel out the radical and leave me with y plus 1. And if I cube the other side, I have x cubed. And then all I have to do is then subtract that 1 from over on the right-hand side, bring it to the left, and then write it in terms of y. So y is equal to x cubed minus 1. And then if I wanted to actually write it in function notation, I would write it f inverse of x equals x cubed minus 1. So here's what that would actually look like if we graphed it. Now you could type it in your graphing calculator, and you may remember that this is one of those cube root graphs, and since it's x cubed minus 1, that means it actually has been moved down 1, and so it's actually going to cross here, and it's going to look something like this. So if we wanted to know the range and the domain of the inverse, well, first of all, if we looked back at the original, and when we studied the cube root functions, we said that the domain was all real numbers and that the range was all real numbers, because you can plug any number in and cube root it. You can cube root positives, negatives, whatever, and you can get positives and negatives and 0 out of it. So it's all real numbers. Well, that means if these switch around, that means that the domain becomes the range and the range becomes the domain. So the range of the inverse is all real numbers, and so is the domain. But we could really tell that by looking at the graph, because as you look left to right, which is what tells you the domain, there is no breaks in the graph. And as you look up and down, the graph is continuous going up and down, and so it's all real numbers for both domain and range. And then one way you can check that to make sure that in fact these are inverses of each other is you could graph both of them and see if they are reflections over the line y equals x. So when I went ahead and did that, and so I can see that here is the inverse, that's the x cubed minus 1, and then we have the original, which is the one right here. Oops. And then of course you can see the line y equals x, and you can see that that is in fact that line of reflection of the two graphs. So that's just another way to verify. Let's go ahead and turn the page and we'll look at another way to tell if relations are inverses of each other. I mentioned earlier in the lesson that we would have another application of composition of functions. So it turns out that you can actually use composition of functions to provide supporting evidence of a claim that two relations were inverses of each other. So we've looked at one way to know if relations are inverses of each other. You could graph them and see if they are reflections of each other over the line y equals x. That's one way. A second way would be maybe if you took one of the relations and you went through the process of switching x and y and solving back for y and see if you actually do get the other relation. Under composition of functions, we can tell if two of relations are inverses by combining them. And if when we combine them under composition, both directions, and that means if we do f of g of x, as you see here, and g of f of x, if the output for both compositions is x, then that means that the two relations must be inverses of each other. So if you combine them under composition of function operation both ways, f of g of x and g of f of x, and you get x, then that means they must be inverses. So we mentioned in the last lesson that composition of functions is not commutative, but this would actually make them commutative, because if we combine them both directions and we get the same output, then in this one special case, composition of function is commutative. So here's an example of two relations, and they turn out to be functions in this case, and we want to know if they're inverses of each other. F of x is equal to 3x, and g of x is equal to 1/3 x. Now, notice we don't have that second function written in function notation, like f inverse of x, because if it was written that way, then we would know it was the inverse of x. So we don't know that it is, and we want to see if it is. So again, we've talked about the other ways that you can tell. But here's a look at how we can use algebra and composition of functions to tell. So if we do f of g of x, that means we take this function g of x and we substitute it in for x in the function f of x. It would look like this: 3 times 1/3 x, which turns out to be x. And if we went the other way, and this time we did g of f of x, and that's where we took the function f and we plugged it in for x in the other function, it would look like this: 1/3 times 3x, which again is just x. So when the output of the composition in both directions is x, that means that the relations must be inverses of each other. Because inverse functions undo each other, when you compose two inverses, the result is the input value x. Because basically, that just undoes all of the operations of the particular relation, and you just end up with just the variable x. Let's take a look at an example of a couple relations that we might want to see if there are inverses of each other. So in example A, I have f of x, which is 3x minus 1, and I have g of x, which is 1/3 x plus 1. So I'm going to start off by looking at the first direction of composition, which is f of g of x. So that means I'm going to take g of x, this whole function, and I'm going to take and put it right in where I see x in the other function. So it would look like this. Wherever I see x, I'm going to put in place of it that function. So I'm going to substitute in 1/3 x plus 1. Well, then I have to simplify this by distributing the 3 through. So that turns out to be 1/3 times 3 is 1, so that's 1x, or just x. 3 times 1 is 3, and then minus 1, so this turns out to be x plus 2. Well, we said it had to be equal to x, not x plus 2, and so basically what this is telling me is that these two things, f of x and g of x, are not inverses. And in fact, there's really no reason to test the other direction, because if it doesn't work one direction, it's not going to work the other direction. It has to work both ways. The output has to be x in order for them to be inverses. Oops, it says is inverses. They should say they're not inverses. Let's make example B a you-try question. So you want to examine the composition of functions f and g. So you can start off with f of g of x, and if you get x as an output, then try g of f of x and see if you get the same thing. So please pause the video now and try to use composition of functions to check to see if these two relations are inverses of each other. So if you gave that one a try, you saw that once again, these are not inverses of each other. We got close, even closer this time. This time, f of g of x turned out to be 1/2 x, but that still does not equal x. It has to equal exactly x, and it doesn't. It really doesn't matter if we try the other direction now, because both directions have to equal x for them to be inverses. Let's take a look at another one together. So this time, example C says f of x is equal to 1 over x minus 1, and g of x is 1 over x, and then plus 1. So I'm going to test to see if these are inverses by doing composition. I'm going to start off with f of g of x, which means I'm going to take this function, g of x, this whole thing, and I'm going to plug it right in the bottom there where there's x. So it's going to look like this, 1 over, and in parentheses there, I'm going to put, right where that x is, I'm going to put 1 over x plus 1. I'm putting the whole function in. Well, that turns out to be 1 over, well then I can put these, the plus 1 and the minus 1 together, and those cancel each other out, right? So those are gone, and that just leaves me 1 over x. Well, 1 over x is just x. Finally, we have our first one that equals x. So we're halfway there. We don't know for certain, but at least the one direction works. So this time, when we have g of f of x, now we're going to take the function f of x, this function right here, 1 over x minus 1, and we're going to substitute it in for x in the other function. And so that's going to turn out to be the denominator there where x is. I'm going to put this whole thing in there, 1 over x minus 1. And then it was a plus 1. Well, when I take 1 and divide it by 1 over x minus 1, if I change that to multiplication of the reciprocal, this whole thing right here just turns out to be x minus 1. But then we also had that plus 1 off the end, and that turns out to be x. So we've got another one that turned out to be x. So the other direction, both directions turn out to be x. And so in this case, I can say that these functions f and g of x are inverses. So our first pair of inverses. And there you go. And how about another you try? So we'll leave example D as a you try, so pause the video and then tune back in real quick and we'll check our answers and we'll be done for this lesson. So pause the video now. Well, so once again we see that f of x and g of x are not inverses. I didn't even bother trying the second direction. Clearly this f of g of x did not turn out to equal x. So that actually does it for today's lesson. So I will see you in class.